Hi everybody, Mrs. Pesic here. We are continuing our look at section 3.4, exponential and logarithmic equations. And we are going to start by solving 6 times 2 raised to the t plus 5 plus 4 equals 11. We have to solve for t. We want to know what value t would make this equation true. Let's start by subtracting 4 from both sides. So we get 6 times 2 raised to the t plus 5 equaling 7. Then divide both sides by 6, so I get 2 to the t plus 5 equaling 7/6. And now, to solve for t, I'm going to have to rewrite this from exponential form into log form. So that's going to be log to the base 2 of 7/6 equals my exponent of t plus 5. And my last step would be to subtract 5 from both sides. So I think my answer would be t equals log to the base 2 of 7/6 minus 5. So that's my exact answer. And if I want a decimal approximation, I can enter that into the calculator, which, let me do that now. Documents. I'm going to a calculator page, and I am doing log to the base 2 of fraction template 7/6, and I need to get out of that and do minus 5, and I want the approximate answer to that, and I'm getting negative 4.78 approximately. All right, let's take a look at another example. If we're solving e to the 2x minus 7e to the x plus 12, I would encourage you for this problem to do a little substitution. Like, let's let u equal e to the x. If u is equal to e to the x, then really think of this e to the 2x as e to the x quantity squared, and I'm going to be plugging in u right here. So far I have u squared, and then I've got minus 7 times e to the x. Again, that's e to the x is like a u, so I've got minus 7u plus 12 equals 0. And now we're going to solve this using product sum. So after we factor this using product sum, we would have, let's see, I need a 3 and a 4, and both of them negative. And so I end up getting u equals 4 and u equals 3. But keep in mind, that's really e to the x equals 4 and e to the x equals 3. So to finish this off, because we are trying to solve for x, we are going to take each of these and rewrite them in log form. So I get x, let me start again, log to the base e of 3 equals x. So that means I can write x as ln of 3, because that's what log to the base e of 3 means. And this one, same deal, this would be log to the base e of 4 equals x, or x equals ln of 4. So I have 2 solutions for this problem, ln of 3 and ln of 4. Let's take a look at this one. If ln of x equals 2/3, remember that's the same as log to the base e of x equals 2/3. And so I'm going to rewrite this one as e to the 2/3 equals x. That's my exact answer, and of course you can get a decimal approximation for that with your calculator. All right, let's take a look at this one. We have log to the base 4 of 3x plus 2 equals log to the base 4 of 6 minus x. I notice that I have log to the base 4 on both sides, and that means that what I'm taking the log of must be equal to each other. This is that one-to-one property, so 3x plus 2 equals 6 minus x. I'm going to solve this, just a nice linear equation. I'm going to add x to both sides and subtract 2 from both sides. So I get 4x equals 4, and dividing by 4, I get x equals 1. And you can plug those in to see that it is true. All right, and let's take a look at this problem. This one says log to the base 3 of 5x plus 13 minus log to the base 3 of 6 equals log to the base 3 of 3x. For this particular problem, I would probably try and rewrite this left side using one of our properties of logarithms. So I would have log to the base 3 of 5x plus 13 over 6 equals log to the base 3 of 3x. And in this case, again, property of logarithms, I've got log to the base 3 equals a log to the base 3. So that means that these expressions here must be equal to each other. So I can say 5x plus 13 over 6 equals 3x. And I'll let you finish this one up because it's a nice linear equation to solve. Dot, 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 you finish that one up. Let's take a look at this one. This one says 6 plus 3 times ln of x equals 4. And this one says approximate to 3 decimal places. So if we subtract 6 from both sides, we get 3 ln of x equals negative 2. Divide both sides by 3, and I get ln of x equals negative 2/3. And so now I would rewrite that in log form as log to the base e of x equals negative 2/3. And then I would write this in exponential form to solve for x. That would be e raised to the negative 2/3 is equal to x. That's my exact answer, but again, you're asked to use a decimal approximation. So I'll let you finish that one up. Let's try this one. For this one, we are solving, this is problem number 16. This is log, 3 times log to the base 4 of 6x equals 9. I would start off by getting rid of that 3. Divide both sides by 3. So now I have log to the base 4 of 6x equals 3. And then to solve this now, I would rewrite it from log form into exponential form. So that would be 4 raised to the 3rd equals 6x. 4 to the 3rd is 64, and then divide both sides by 6 to get your answer. So x is equal to 64 over 6, which would be 32 over 3, and so whatever that is, 10 and 2/3. All right, let's take a look at this one. This one says log to the base 10 of x plus log to the base 10 of x minus 9 equals 1. Again, I would rewrite this using my properties of exponents. So I would say x times x minus 9. Okay, and that means this would be 10 raised to the 1 equals x squared. I can multiply this out first. This would be x squared minus 9x. So I really have 10 raised to the 1st equals x squared minus 9x. And I would subtract 10 from both sides, and I have a quadratic equation. That's not good. I've got a quadratic equation to solve, so x squared minus 9x minus 10 equals 0. And this factors here. I need a 10 and a 1 and a minus and a plus. And so then we're going to set this equal to 0 and this equal to 0. And I would get x equals negative 1 or x equals positive 10. Let's go back up and see if those solutions that we got will work in the original problem. All right, if I plug in negative 1, like I am right here, this is me doing a little check. I get log to the base 10 of negative 1 plus log to the base 10 of negative 1 minus 9 is supposed to equal 1. Well, does anybody see a problem? Well, right here, because we're not allowed to do this. So negative 1 cannot be a solution. We will call that an extraneous solution because it's working in our little quadratic equation here, but it doesn't work in the original. And we could try 10. So if I do log to the base 10 of 10 plus log to the base 10 of 10 minus 9, which is 1, is that equal to 1? Question mark. Well, log to the base 10 of 10 is 1. Log to the base 10 of 1 is 0. So I get 1 plus 0 equals 1. So 10 does work. That's our only solution for this problem. All right. All right, let's take a look at this example. You have deposited $1,000 in an account that pays 6.25% interest compounded continuously. How long will it take for your money to double? So as soon as we see compounded continuously, that means we're going to use that PERT formula that looks like this. Our principal is 1,000, and we're going to multiply that by e raised to the rate, which is 0.0625. We don't know the number of years. We're trying to decide the number of years that it takes for our money to double. So that means that we would have 2,000 at the end of the time period. So at this point, we're going to divide both sides by 1,000. So I get 2 equals e to the 0.0625t, and I need to solve this equation. It's currently in exponential form. I'm going to need to write it in log form. So that would be log to the base e of 2 equals 0.0625t. You know that log to the base e of 2 is ln of 2. So I am going to solve this equation by dividing both sides now by 0.0625. So let's try this on a calculator. I want ln of 2 over 0.0625. ln of 2 divided by 0.0625. So it's going to take approximately 11 years for your money to double at that interest rate. Okay? Okay, let's take a look at this example. The number y of endangered animal species on a protected wildlife preserve from 1990 to 2004 can be modeled by this natural log equation, where t equals goes from 10 to 24, and it represents the year, with t equaling 10 corresponding to 1990. During which year did the number of endangered animal species reach 342? So we're going to plug in 342 for the y. Right, so the y is representing the number of animals, endangered animal species. So 342 equals negative 117 plus 159 times ln of t. I would start this off by adding 117 to both sides. And when I do that, 342 plus 117 is, doing this in my head, hopefully this is good, 459 equals 159 times ln of t. I would then divide both sides by 159, and so I've got 459 over 159 equals ln of t. Remember, that's the same as log to the base e of t, and so to solve for t, I would rewrite it from log form into exponential form. So I would write it as e raised to the 459 over 159 equals t. So on our calculator, I want e, not that, e, no, delete. I want e raised to the power of 459 over, it was 459 over 159. And so that would be about 17.9, about 18. So the answer to the question, during which year did the number of endangered animal species reach 342? I'm going to go with t equaling 18. And since t equals 10 represents 1990, then I would say this would correspond to 1998 as my answer. All right. Okay, that's it for this lesson. I am going to ask you to watch a lesson on section 3.5, and have a good day.